Hello guys, this is our question. It says one end of a uniform meter stick is placed against a vertical wall. See Fig P11.70. The other end is held by a lightweight cord that makes an angle theta with the stick. The coefficient of static friction between the end of the meter stick and the wall is 0.40. What is the maximum value the angle theta can have if the stick is to remain in equilibrium? Okay, so on that question, guys, what we will do there is we first have to see which forces we have in the x direction and which ones we have in the y direction. Looking at this tension, we know that it will have two components because it's in between the minus x direction and the positive y direction. It's in between, right? So it's actually in the second quadrant, right? So it's like this. So what it means is that we can resolve it into t sine theta and t cos theta, right? Now, if we say summation of forces in the x direction, right? Which forces do we have in the x direction? They are balanced. That's why in the x direction, this thing is stuck to the wall and it's not going into the wall, right? So by Newton's law, Newton's third law, there is an action there of the, it's the component of the tension acting in the, on the meter stick, causing the meter stick to press against the wall and the wall will press back. So that's Newton's third law there, right? Action reaction forces. So we can say that we have n minus this one that's going there, which is t cos theta. This is equal to 0, right? It's not equal to ma because we don't have an acceleration there, towards any direction. The net force is 0. So we have that equation. So n is equal to t cos theta. We can also write that the friction, so let's call this equation 1, right? The friction F is equal to what? Mu n, right? So F is equal to mu t cos theta. That's the friction. Because remember, the frictional force has to go upwards since this thing has a tendency of sliding down. You cannot say it will slide upwards because its weight is acting on it. So it has a tendency on this side of actually sliding down the wall. So the friction acts in that direction in that case. So we have friction equals that. We can say this is equation 2. We can also say summation of forces. Let's not start with moments. Let's say forces in the y direction equal to 0, right? Because this thing is to remain in equilibrium in all directions. So we're going to have friction acting upwards, and we add this to t sine theta, also acting upwards. We say minus the force that's acting downwards is the weight of that thing. So F plus t sine theta. So this is equal to 0, right? So F plus t sine theta have to be equal to mg, the weight of the meter stick itself. Let's call this equation 3. Now we take moments. Let's say sum of moments taking positive to be clockwise, right? Let's take moments about this point. Let's call this point, we could call it A. Could say that's point A, right? If we take moments about point A, right, we are saying they're equal to 0. This is a meter stick, which means it's 1 meter long, right? Since it's 1 meter long, it means this force has a perpendicular distance of half a meter from the pivot, right? This one has a distance of 1 meter from the pivot. So we're going to say mg multiplied by 1/2, which is for half a meter, right? That's the moment, and it's a clockwise moment. That's why we put it as a positive. Then we say minus t sine theta times 1. That's just t sine theta. Those are the two forces that can cause moments, because these ones that are at the pivot, we don't count them. They don't cause any moments. This is equal to 0. So that means t sine theta, right, is equal to what? 1/2 mg, right? That's what we can write. We can also then write that t sine, we got t sine theta, right? We can also say t is equal to what? it's equal to 1 over 2, so it's actually mg over 2 sine theta, right? So we could say this is our equation 4, right? Then now we have equation 2 and equation 3, right? We know that f is that, so we can just put mu t cos theta there, right? Then we also know the value of t and the value of t sine theta. So in this equation again, we can do this. We have mu t cos theta for the friction. Then for t sine theta, we have half mg, because t sine theta is half mg, right? Then we also have what we're saying, this is equal to what? To mg, right? Then here where we have t, we can substitute mg over 2 sine theta. So mu mg cos theta over 2 sine theta plus 1 over 2 mg. But since we have half mg and mg, we could simply just take that to the other side. It will become mg minus 1 over 2 mg, right? So we now have that. So we can cancel that and that and that, which means here we will get 1, right? Because it's everywhere. So we're going to end up having what? 1 minus half on this side, and on this side we have mu. Here it will be cos theta over sine theta. It's mu cos theta over 2 sine theta actually, because we have that 2 there, right? So we have mu cos theta over 2 sine theta. We are saying this is equal to what? We are saying this is equal to half, because we have 1 minus half on this side, since the mg is cancelled. So we now have that. We can then cancel that and cancel that, right? Because it's 1 over 2. It's 2's that are both on the denominator. So we will end up with something like mu cos theta over sine theta is equal to 1, right? Then if we multiply both sides by sine theta over cos theta, we see that this becomes what? 1, right? Because it will cancel with the sine theta and then with the cos theta, right? And then also on this side we multiply by sine theta over cos theta. On this side we said it will cancel, right? So we'll end up having 1 times sine theta over cos theta. That's just mu is equal to tan theta, meaning theta should not be greater than arctan of mu. So it's arctan of mu, right? So we'll end up getting theta should not be greater than, theta should always be less than or equal to a tan to the minus 1, right, of 0.4. You guys can go ahead and calculate that angle and see what it gives you.